So once we've performed saponification, we end up with the salt of a fatty acid. And what we want to do is test the cleaning action of a soap, or figure out how they actually clean. Remember that grease is basically long chain non-polar hydrocarbons. Okay, non-polar. So they don't go well, or they don't dissolve in polar water. Water is polar, it won't dissolve these dirt and grease molecules. When soap is dissolved in the water, the ions that make up the soap dissociate. And the soap, remember, the ions were the salt of a fatty acid. And you can see here our salt of a fatty acid. It has the negative molecule, negative ion, and the positive sodium ion that was produced in saponification. It will dissociate in water to produce this, and long chain fatty acid ion and our sodium ion. This negative fatty acid ion is what we call a surfactant. It's a surface acting agent, and the positive ion doesn't play much of a role in the cleaning. Plays no role, in fact. The negative ion, the long non-polar hydrocarbon chain tail, has an anionic head, a charged particle on the end of it. You can see here the long tail is non-polar. It's what we call hydrophobic, and the anionic head is negatively charged. This part of the molecule, it's COO minus, the anionic head, is a negative charge. It is polar. So one part of this molecule can dissolve in water, the other part can dissolve in grease or oil or fats. A soap has a non-polar end. It dissolves in non-polar fats and oils, and the polar end dissolves in water. Forms groups of soap molecules called micelles. You might have seen on a TV ad, they're talking about micellar soaps, micelles. Micelles, basically, here's the diagram. You can see here the polar anionic head and the fatty acid chain here. This is the part that makes it a fatty acid, and that's the chain. It's non-polar, straight, hydrogens on both sides, carbons down the middle. This end here is charged and polar. You can see what happens when they get in water. They form into groups. The anionic polar head on the outside and the non-polar tail in the center. That tail can dissolve into grease and oil molecules, globules, and it acts like it's a surfactant because it's attaching the surface, but it also acts like an emulsifier. An emulsifier is something we'll see shortly, can break the oil up or break a liquid up so that it is suspended in another liquid. If oil is added to water, we say that's immiscible, they don't mix. And because of that, when you get grease on your clothes, they can be difficult to get off. The oil and grease stains often stay for a long time because it's difficult to get off. So soaps are compounds which act as emulsifiers. This means they help the oil and water to mix. One liquid becomes mixed with another, not dissolved, mixed, suspended, emulsified, we call that. Dissolving into the oil and surrounding the oil globule and bringing it up. If the oil is stuck firmly to the fabric, these tails will attach to small pieces, then they'll be carried up, and this part will be bonded as it's polar to the water molecules. So you've got this negative part will bond onto the H hydrogen of the water molecules, slightly positive part, this polar water molecule. So that's how they sort of work. They work on the surface They attach to through the non-polar, dissolving in the non-polar oil, non-polar tails, lifting it up, and the anionic head, the polar part, will carry off and attach to the water molecules. Okay, a surfactant lowers surface temperature of water, so it disrupts the hydrogen bonds between the water molecules, so it increases the ability of water to wet a surface. Here you can see some grease and some water molecules around the outside. When you add surfactants, surface acting molecules such as our hydrophilic heads and our hydrophobic tails, so our anionic head, we get this effect. The anionic heads can attach to more water molecules and bring them around and attach to all sides of the grease globule, the grease part. It spreads the water out over it. Here, the surface tension is greater. Here, it's less. It's been allowed to spread out. Surface tension is like a force holding this in a small drop. And here you see a little bit better diagrammatic representation of these soap molecules. The polar head, the anionic head is negative. The non-polar tail, which can dissolve into those. The tail we call hydrophobic. It's phobic, as like arachnophobia. It's afraid of water, doesn't like to mix with water, prefers to be away from water. It's not attracted to the water molecule, which is polar, has a positive and a negative part. The polar ionic head is hydrophilic, so up here it's charged. It attaches to water, it's attracted to water, it's electrically charged, so it can be attracted to those water molecules. So when surfactants are added to water, they don't tend to spread evenly through the water. They sort of clump together with the negative heads pointing outwards towards the water molecules, and the tails head together. They sort of clump together, and this forms a suspension in the water. It's an emulsion. It's not a solution. It's not dissolved in the water. These aren't spread out throughout the water. They're attached together like a small, very, very small micelle, we call. And that's a suspension. So an emulsion is a suspension of one liquid in another. So when you agitate the water, when you shake it around, the hydrophobic tail attaches itself to grease. So a washing machine does this agitation. It moves the water backwards and forwards, allows the hydrophobic tails, that's the tails that are attracted to the grease, the non-polar tails, they attach to the grease particles by dispersion forces. And you can see that what a dispersion force is earlier. The head, the hydrophilic head, the water-loving head, water-loving, is dissolved into the water. So this is how it forms. Tails, non-polar, dissolve in the non-polar grease. Polar heads, hydrophilic heads, attached to the water molecules. And you get these surfactant clumps, and then when you agitate the water, they go down, they can mix and attach to the grease with their non-polar tails. These are our clothes, and then they are brought up one at a time. As the waters swell around, it pulls the grease off the fabric, and those polar heads, anionic heads, surround the grease and keep it suspended in the water. It doesn't necessarily have to go back down into the clothes. Surfactants are things that keep the grease suspended as an emulsion up in the water. Okay. Clothes continue swelling, the grease is suspended, the water sort of turns a grey colour. It's called grey water. Soap, water and grease together form that emulsion. And a surfactant anion acts as a bridge between the oily particles and the water. That's these parts. They're like a bridge between them, keeping them suspended in the water, suspended, floating in the water, not on the surface necessarily, but floating, distributed throughout the water. And here we see an example of that in motion. Surfactant ions, our soap particles, the tails, are going to dissolve into the grease when their agitation occurs. Here they go. Enough of them spread around the grease. They break it off into clumps surrounding it. As the water can now wet the grease molecule completely around the outside, it heads off up into suspension. Remember, these heads, anionic heads, are hydrophilic. They love water. They're attracted to the water. These tails are non-polar, and so they're dissolved into the grease. They're holding the grease particles together, and we end up with a clean surface. Detergents are a little bit different to soaps. A detergent, the word is it means a cleaning agent. They're like soaps. They contain surfactants, surface acting agents that clean our clothes, that remove oils from our clothes. However, soaps and synthetic detergents both have that soluble part, water soluble part, that polar part, and that oil soluble end, and they both clean in exactly the same way. They can be distinguished by their structure and their chemical composition. Also, they have a slightly different effect in hard water. You remember that soaps didn't lather, make bubbles, make foam very well in hard water. I remember hard water was my good car, water with lots of magnesium or calcium ions dissolved in it. So what are the differences? How are they different? Soaps, they're made from vegetable oils, fatty acids in animals, beef oils. Their composition, they have sodium or potassium salts, so they have that alkanoic acid end, the COO, with the minus and attached to something else, sodium or potassium, usually from sodium hydroxide or from potassium hydroxide. Detergents are made from hydrocarbon chains. They're from petroleum. That's a disadvantage, and you can talk about the disadvantages of using petroleum, a finite resource. It has to be refined and then down to a certain hydrocarbon chain, catalytic cracking, fractional distillation, all the way down to a certain chain that they need for these molecules. Usually the hydrocarbons have a sulfate or a sulfonate end, so it's a different end on it, and we'll see that shortly. The structure, the soaps are ionic or polar end with a non-polar tail, similar to the soap. So the soap is similar to the detergent. The heads are head anionic, or other heads we'll see in a minute, and a non-ionic polar, non-polar hydrocarbon tail. It can be anionic, so minus in the case of the COO, minus part of that soap molecule, or it can be cationic, so it could be positively charged head on it, or a non-ionic part, and we'll see those shortly. How are they made? Soaps, saponification, remember from previous. You're heating fats or oils, esters, and you're heating that with concentrated or fairly strong sodium hydroxide to produce that salt, to remove the glycerol from the fatty acids. You also could use potassium hydroxide. You get that precipitation of even more of the sodium salt or salt of a fatty acid with strong brine solution or concentrated sodium chloride. The detergents, similar in soap, it's an alkanol from petroleum, so quite a long alkanol, reacted with sulfuric acid, which can be a dehydrator, and that forms the sulfonic head. It's reacted with sodium hydroxide to form sodium sulfonate. In hard water, how do they both fare? Well, soaps don't lather well. We know that. We've done some testing of that. We've seen tests of it too. If you've got calcium and magnesium ions in the water, it's hard, it doesn't lather, instead it makes this scum that floats on the water, and it doesn't help the clothes. It sort of turns a dull grey colour. That's a disadvantage of soap in hard water. In hard water, our detergents can lather. They don't precipitate those mineral salts, the calcium and the magnesium salts, out into a precipitate. Are they biodegradable? Yes, soaps are biodegradable. They have no phosphates, and they're not really soluble. That's a disadvantage. They deteriorate with age. Our detergents, however, biodegradable if hydrocarbon chain is straight. If it's branched, they're non-biodegradable. If they can be mixed with phosphates that pollute the environment, so our phosphates can add to our problems in water quality. We'll have a look at those we had a look earlier at those phosphates. Phosphates can cause growth of plants and things, organisms, and we'll see, you can go back and have a look at that. Soluble in water, don't deteriorate with age. They're stable, so they last for a very long time. So here's our structure of surfactant molecules in detergents. So not soaps anymore. Soaps are very similar to the first version. You can have anionic, cationic, or non-ionic. Our anionic one has a negative end, a polar end, and a non-polar tail. Works the same as the soap. It can be cationic. They can have a positive end, head, and a non-polar tail. Or they can have a special type of structure that's non-ionic. So there's no charged head, but the head still can have an effect on oil molecules, grease molecules. So the first case, the anionic molecules, surfactants from detergents, they're the most widely used. They're used in dishwashing liquids, laundry detergents. Their particles have a negatively charged head. So it's very similar to the COO minus head on the soaps. The most common have a long hydrocarbon end, and they're obtained from petroleum. So they have to undergo cracking, distillation. And the ionic end is sulfate, tends to be sulfate or sulfonate ion. So SO4 2- or SO3 2-. Anionic surfactants are high sudsing. They suds a lot, make a lot of bubbles, make a rich lather, and have excellent cleaning properties, especially for fabrics that can absorb water into them, like cotton, wool, silk. Not so good on things like nylon. The hydrophobic end and the hydrophilic end. The hydrophilic is the water-loving end because it's charged, it's polar. This is non-polar, so it can interact with the oil molecules. The other type, cationic surfactants, they're detergents made with particles with a positively charged end. Usually the positive part comes from an ammonium compounds, so that's NH3, often with a H substituted for carbon groups. They're used as cleaners, fabric softeners. The positive charge can adhere to the fabric, which quite a lot of fabrics have a negative charge. If you remember, silk is used to rub electrons. Correction. So cationic surfactants are detergents made of particles with a positive head, different to the negative head of the anionic detergents. They're usually ammonium compounds or compounds derived from ammonia, NH3. They use its cleaners, fabric softeners. Their positive end often attaches to the fabrics, and that usually carries a negative charge, the fabric, and that reduces static, so the cling that you get from some clothes. They can act as germicides, kill bacteria, some forms of bacteria. The ammonium ion part, the cationic end, can disrupt the cell walls of some bacteria. They can be used in mouthwashes, nappy washes, antiseptic soaps. They're not used in dishwashers because glass has a similar charge to clothes, and they tend to attract the positive heads to the glass, making the glasses slippery, not that squeaky clean feeling. An example of this one here, quaternary ammonium detergent, and you can see the end there that would have formed that comes from ammonia compound, that NH3, and here you've got other groups put in instead of the ammonia group, the H's from ammonia. The other type of surfactants are non-ionic. They have a hydrophilic end with many oxygen atoms that form hydrogen bonds with the water. So they're not charged, they're not negatively charged, attract to the hydrogen, or positively charged, attract to negatively charged molecules. They're a hydrophilic end that is, because it has lots of oxygen atoms, it forms bonds with the water, not charged. Okay, so it's still polar but not charged. They don't ionize in water, and they're low sudsing, so they don't make a lot of foam. They clean fairly well, so they're used in detergents for laundry, for automatic dishwashers, for car cleaning, for cosmetics, and they're often used in froth flotation, so to bubble impurities to the surface. You can see the shape of those. Low sudsing, because in an automatic dishwasher you don't want lots of suds. And you can see the diagram here. Non-ionic end, the polar alcohol group, so it's alcohol ethoxylate, lots of oxygens attached. Okay, lots of places where the hydrogen from the water can attach to a bond to. Here you can see this end is non-ionic, and that's our end that would dissolve in the detergents. So what are the impacts of using soaps and detergents? Well, as we've seen, soaps are biodegradable, so they can be broken down by microorganisms, and they form smaller naturally occurring molecules, not the longer chain salts or fatty acids. Modern detergents, although they're still produced synthetically, can be broken down by microorganisms, and so are considered to be biodegradable. They must be able to be broken down. Phosphates are a problem. Although they can remove hard water minerals, they can form a precipitate with magnesium, calcium. That increases their effectiveness. As a deflocculating agent, that is, they prevent dirt from settling back into clothes, so they keep it floating up into the water column, the water level. They're relatively non-irritating, non-toxic in the environment, but phosphates, again, can contribute to eutrophication of water. So make sure you look back at eutrophication and look at that. It can cause rapid growth of algae blooms that decrease light down into the lower levels of the water, and can cause that eutrophication, that increased biological demand of oxygen. Major laundry detergent manufacturers no longer use these phosphates in their formulations because of their effect on the water supply. How do they get in the water supply? Non-processed sewage, or running out straight from washing cars, washing driveways, washing houses, washing roofs, washing things, and the water's left to go down into stormwater drains. That goes into the water, and out into the rivers and estuaries. Okay, they're also used for artificial fragrances in soaps and detergents. They're made from petroleum, so the artificial fragrances come from petroleum esters. Many don't degrade in the environment, and they can have a toxic effect on fish and mammals. On us, they can cause allergies, skin irritations, or eye problems. If you look on the labels of many soaps with fragrances and artificial additives, they tell you not to allow it to get on your skin or your eyes. Often soaps and detergent have optical brighteners, which are chemicals that tend to reflect UV, reflect light, and make the clothes look whiter. Okay, they don't readily biodegrade. They stay on the clothes after they're washed. They're toxic to fish, and they can create mutations in bacteria, so that's not a good thing. They can cause allergy and skin reaction when you touch them on your skin. Not good if you're highly allergic to those sort of things. Anionic detergents can make quite a lot of foam. This can, if foam coats a river or coats, when there's water being stirred up by wind or by rapids or flowing water down rocks, you can get this foam covering, and that can affect the water getting down into the lower levels of the water. So that can cause that eutrophication effects. Cationic detergents can be used as that's the one with the negative end. Correction, the one with the positive end. Cations are positive. They can be used as germicides. That's the one with the usually nitrogen, ammonium compounds. They can disrupt the cell walls of bacteria, and if they enter the waterways, they can have the same effect on other smaller organisms. That affects the food chain and the quality of the organisms that are around for the food chain. Diversity. Thanks. Non-ionic detergents, being biodegradable and producing not much foam, are the best for the environment. Most environmentally friendly of all those detergent classes. So the anionic, cationic, the non-ionic detergents are the ones that are better for the environment for the obvious reasons. Okay, what do we use for soap making? There's a range of things we can use. So tallow used to be used for candles and can be still used. It's a byproduct of sheep and beef processing, meat processing, and it's the most common sort of animal fat that's used in soaps. And remember, that's a glycerol with long chain fatty acids attached. Coconut oil is a common used one from dried fruit from coconut palms. We're just going over a few things. The emulsion is a mixture of two liquids that are dispersed and is suspended in one another. So if you think of shampoo's often an emulsion, it has surfactants in it, emulsifiers. We'll see one shortly that we can produce. Soap, water and oil form an emulsion. So if you have oil and you have water and you mix the two, oil and water, you shake it up, it will separate. But if you put a soap mixture in there, it can act as an emulsifier, attaching, as we saw, as a surfactant for the oil and spreading the oil out through the water layer. So the soap acts as an emulsifier. So that's mayonnaise is a typical one that you can make, which is just oil with egg yolk as a surfactant. It has materials in it that act as a surfactant. Some lemon juice, those usually oil and lemon will separate, or oil and vinegar. Put the egg yolk in, it has an emulsifier in it, and it stabilizes that structure so that when it's mixed up, the oil and the vinegar and that mixed together. So that's how mayonnaise is used. That's the typical one that we can make in the classroom. And here's the example of it. And the emulsifier in the egg yolk is called lecithin. It has a polar and non-polar end, and it attaches to the oil, the non-polar end. The polar end attaches to the water, and as a result, those droplets of oils can be dissolved into the water or into the vinegar or whatever it is that you're using to make the mayonnaise tangy. And it stays together, it doesn't separate into the oil and water part. So it has that surfacting and emulsifier acting on it. And here's a quick recipe for you to try at home. If you do this, you'll remember it much better. And you've got egg yolks, oil, lemon or some other solution with water in it. The surfactant is in the egg yolk, not the egg white, just the yolk. So we put the egg yolk into a cup, add our lemon, and then slowly pour the oil in and stir and beat while we're doing it. The oil is emulsified, broken up by the lecithin in the egg yolk, and it makes an emulsified solution. Mixture, sorry, not solution.